In this lesson, we're going to take a look at a few memory tools to help remember some of the periodic trends. Specifically, trends related to atomic radius, ionization energy, electronegativity, and electron affinity. Let's briefly look at a definition for each of these terms or trends. Atomic radius might be thought of as the distance from the nucleus to the valence electrons in an atom. Atomic radius is affected by a few ideas. In a previous lesson, we looked at the ideas called nuclear charge and shielding. These two ideas affect the trends that we're looking at in this lesson. Again, what we're trying to do is develop a simple memory tool for remembering these trends in this lesson. The largest of atoms would tend to have the most energy levels, or rings, of electrons, if we were viewing them as what we know as the Bohr models. Therefore, the largest would be on the lower left side of the periodic table. When we look at the right side, we must exclude the noble gases. One of the reasons for excluding them when we look at atomic radius has to do with the number of valence electrons in that outermost energy level. In most cases, we would have 8 valence electrons, or a very crowded region of valence electrons. As we have more valence electrons, there would be more repulsion between those electrons, meaning they would push each other further apart, creating rather large or larger atoms. This may be thought of as one of the reasons that we exclude them in these periodic trends. When knowing where the largest atoms are, the smallest atoms would be in the opposite corner, again excluding the noble gases. So our smallest would be in the top right region. Therefore, I like to use the terms large and small. Large meaning lower left, beginning with L, makes it easy to remember. Small is the opposite corner, top right. Therefore, comparing random elements, we can sometimes use their position to simply understand a comparison of their radius. Let's circle a few atoms to compare in rank and radius. We'll circle beryllium, calcium, carbon, and cesium. If we'd like to place these in an increasing order, meaning smallest to largest, we would look at our periodic table and our memory tool that we've created. The smallest of each of these would be the element carbon, since carbon is furthest to the right and closest to the top compared to any of the other elements. Next in line would be our beryllium, because it has the same number of energy levels as carbon. Then we see calcium with more energy levels. And finally, cesium, the largest of them. We have an increasing order from smallest to largest: carbon, beryllium, calcium, cesium. By writing the terms large, small on a version of a periodic table and excluding the noble gases, it creates a simple memory tool for remembering this periodic trend related to atomic radius. Let's take a look at the next trend, known as ionization energy. To define an ionization energy might be thought of as the energy needed to remove an electron from an atom. In order to remove electrons from an atom, we would need to have a specific amount of energy required to do that. That amount of energy is affected by the distance from the nucleus. Therefore, larger atoms require less energy to remove valence electrons from. This is because of the attractive force between the nucleus and the valence electrons when atoms are large. This would be a rather weak attractive force. As atoms get smaller, that attractive force increases. The simple memory tool that I like to use for this trend uses the words low, again beginning with L, lower left side, and the opposite of low would be high. Therefore, opposite corner, we write the word or the term high. Again, we exclude the noble gases. Our reasoning for excluding the noble gases is that they already have what we may know as octet, or a completely filled outermost energy level. Let's circle a few random elements to compare in what we would call ionization energy. We'll circle sodium, aluminum, oxygen, and barium. Let's circle carbon. If we'd like to place these in an increasing order based on ionization energy, we want to place a list from lowest to highest in ionization energy. Again, by looking at position, we can kind of tell where the lowest ionization energy would be between these four elements. The further to the left on the periodic table, the lower the ionization energy would tend to be. Therefore, sodium would have our lowest ionization energy. Sodium aluminum, being in the same period, would allow us to easily compare these two elements. Since aluminum again is closer to the position of low, we would rank aluminum as our second lowest ionization energy. Moving onward, we see that carbon would be next, and followed by oxygen. The simple memory tool of writing the words low in the bottom left-hand corner and high in the upper right-hand corner help us remember the trend or pattern for ionization energy. Let us look at the trend or pattern for electronegativity. Electronegativity will follow the same pattern as ionization energy. Therefore, we can use the words low and high that we've already written on our periodic table. Let's circle a few random elements to compare. We'll compare potassium, boron, fluorine, and beryllium. Recall electronegativity simply relates to the ability to attract valence electrons into a chemical bond. Smaller atoms tend to have greater attraction because of that distance from the nucleus to the outermost energy level. However, we will use the words low and high because it follows the same general pattern as ionization energy. Therefore, we can put our list in rank order. If we're interested in a rank order of increasing ionization energy, we would list potassium as the first element, followed by beryllium, boron, and then the highest of ionization energy, fluorine. The words low and high relate to the positions of the electronegativity on the periodic table. Again, we must exclude what we know as the noble gases when we talk about these trends. The reasoning for exclusion is the attraction for valence electrons of these gases typically is not thought of as a concept that exists to a great extent because of what we have called octet, a stable electron arrangement around these atoms. The general pattern for electron affinity, or the energy change that takes place when an atom attracts a valence electron, follows the same general pattern as both ionization energy and electronegativity. Once again, the words low and high that we have written as our memory tools on the periodic table help us remember this. Therefore, if we circle some random elements, lithium, strontium, phosphorus, oxygen, we could rank these in electron affinity from lowest to highest. Even though strontium tends to be lower on the periodic table, it is not nearly as far left as lithium. Therefore, placing these in an increasing order for electron affinity, we would rank lithium, strontium, phosphorus, and oxygen. To restate how to create the memory tool, simply ignore the noble gases. So we can think of the noble gases as not following these trends. Then think of the terms low and large, meaning low ionization energy, electronegativity, and electron affinity, and large relating to radius or size of atoms. The opposites of the words low and large go in the top right corner, opposite of low being high, opposite of large being small. Recall that large and small refer to size or radius. Low and high refer to ionization energy, electronegativity, electron affinity. This is a good memory tool that will give you a general idea how to recall the periodic trends. One other trend that we have not mentioned yet would relate to the reactivity of metals compared to other metals and nonmetals compared to other nonmetals. In general, these two corners, francium and fluorine, reveal the most reactive of the metallic elements and the most reactive of the nonmetallic elements. In general, The elements that are metallic and are further left on the periodic table are more reactive, and the elements that are nonmetals that are further right on the periodic table are also more reactive. We can use the general location of an element compared to the position of fluorine for nonmetals and francium for metals to identify their general reactivity when comparing. Although exceptions will appear in this is a general way to understand some of the trends or behaviors that allow us to understand how reactive one element might be versus another. For example, if we were comparing the elements sodium to potassium, potassium might be thought of as being more reactive because it is closer to francium on the periodic table. Comparing perhaps the element called nickel to either of these, both sodium and potassium would be more reactive than nickel because both sodium and potassium are closer to francium on the position. While exceptions may exist for some of the trends that we spoke about in this particular lesson, this is a really good tool for trying to generally understand some of the trends that are found on the periodic table that describe the behavior of things related to the size of atoms or how electrons are related to atoms.